whatever time. Who knows? So let's work. You know, I don't feel like I have very many announcements. Today's the last day of the first exam in the testing center. And I think we're winding it down. So raise your hand if you were in the exam last night at 8 o'clock. Yeah. There was a fire alarm. It was exciting. And from my vantage point, that fire alarm that happened at 8 o'clock last night was just a sequence of bad things that had happened during exams. And so I was like, yeah, okay, fire alarm, no big deal. So I hope that they accommodated you appropriately. My understanding was that it all worked out. If it didn't, let us know. You should be right smack in the middle of MP2 at this point. And pretty much everything that we've been talking about is relevant to that MP. So in particular, I'm going to do some things in class today that are specifically designed to give you the information you need to complete that problem. The first part of it, MP 2.1, is very much like MP 1. The second part, though, is just tons and tons of memory manipulation and management. So that's what we're going to be kind of focusing on. If you have not read the spec for MP2 yet, I strongly encourage you to do so. You don't have to, I mean, I'd like you to get started on it now, but you don't have to. But what I really think will help you out is if you at least read the spec now, today. Like, make that your goal today if you haven't done so. So raise your hand if you have read the spec for MP2. Just, this is for my curiosity. Okay, I'm going to go with half. You think half? Okay. I'm going to ask again on Friday. We'll see what that looks like. Okay. So we were talking about the copy constructor. And in the context of our discussion, we were dealing with what now is known to be a fancy sphere. Later on today, we're going to go very briefly back to the stupid sphere. But for now, in the context of our memory discussion, we're talking about a fancy sphere where these are the private members. Now, anytime anybody gives you a class to use, the first thing you do is you look at the public section to see what you can do with that class. So you kind of get a feel for if you're going to use it, what can be done. But probably the second thing you do is you take a look at the memory associated with the objects of that class or the objects of that type. Now in this case, we take a look at it, we go, oh look, there's a cute little double, it stores the radius, that makes perfect sense. And then things seem to kind of get fuzzy, like, I don't know what all of this stuff is about. There's a string, but it's a pointer. I just don't know, and heaven knows what that is. I'm not even sure I want to know what that is. What we have decided upon for this memory is an object that looks like this. It has two fields that are, one of which is a double and one of which is an int. So I'm just going to put some values in there. This third thing that is a pointer is intended to be instantiated not as a single string on the heap, but rather as a linear collection of strings on the heap that we refer to as an array. So this is intended to be an array of strings on the heap, okay? I think we said red, juicy, crunchy is an example of things we might put as data. Now, I have a question, a very quick question for you. Whose responsibility is it to create this structure given these variables? What code is executed that creates this structure for the object? Okay, whisper it to the person sitting next to you, and I'm going to kind of listen. Okay, did you say constructor? I was like trying to feel the room. Okay, so it's the constructors. It's the constructors of the class that take these variables and give them this value. Okay? All right. Last time, we talked about a particular constructor used by the system for you when it needs to make a copy of one of these things. It's called the copy constructor, and its function signature is sitting right there. Okay, so this is the function signature for the copy constructor. Now we know it's a constructor because two things. How do we know it's a constructor? Somebody raise their hand to tell me one of the two things. Yes, Mark.
It has the name of the class.
It has the name of the class. That's right. They match. Kindergarten game, they match. How else do we know that it's a constructor? Yes? No return type. That's right. Those are the two things that are the clues. Okay, fine. Why is the constructor's parameter, the copy constructor's parameter, what does this mean? What words go with that puzzle? Somebody raise their hand. Yeah? Pass by reference. That's right. So why is the copy constructor have a parameter which is passed by reference? Somebody raise their hand to answer. What's the alternative to pass by reference? Pass by fruit. Pass by value. Very good. Okay, so the alternative would be pass by value. It's the only alternative. Okay, we're either going to pass by reference or we're going to pass by value. All right, so what would happen if we pass by value? So suppose not. This is a proof technique from CS 173, right? Suppose we don't pass by reference. What? Yes? Yeah, right, exactly. Think about this a second. If we got rid of this guy, if we, I'll do it in yellow because then it doesn't seem, if we got rid of that and we were passing by value, the way pass by value would be implemented would be to invoke the copy constructor. Well, where's the copy constructor? Oh, wait, we're writing the copy constructor. Okay, so there is no copy constructor yet to be used in the case of pass by value, so it must be pass by reference. All right, so I'm going to write that down in a quick sentence, okay? Why is it? The copy constructor is used to pass by value, and that's what we're defining. Now, of course, if you try to do this, if you try to make a copy constructor that passes by value, the compiler will yell at you because it doesn't have a way of creating the mechanism for making the copy. So it'll say, sorry, by function undefined, there is no copy constructor to make this. You cannot pass by value there, okay? All right, here's another question for you. We've seen the keyword const before. Do you remember where? Do you remember where the const appeared in a function signature when we saw it last time? Yeah? Yeah, in get diameter, right? In a get, in a function where we were getting information. Where did it occur in the function signature? So I'll even write it. I'll write double get diameter. Had no parameters, right? And then semicolon. Where was the const? Do you remember? Yeah? Yeah, at the very end, right? It was right here. So that's different. All right, somebody describe for me what it meant for the const to be right here. What did it mean for the const to be there? It's a promise that get diameter would, yeah? Very good. Not modify the data associated with the class or the member variables, okay? So that's a promise. Well, now we have a situation where const is appearing within the parameter list. It's slightly different. It's the same keyword, but in a different location. This time, it's in reference to this variable, the input variable arig. Yeah? There's no comma, that's just an artifact. Const. There. Is that better? No, there is a space, but it doesn't matter. There doesn't have to be a space. There can be a space, but it doesn't matter. Okay, so this new const, however, is a modifier for the parameter itself. And it is a promise that the code associated with the copy constructor in this case, or any function, will not change the value of that parameter. Now this is a safety feature, right? Because remember, we're passing by reference, which means arig is not new. It's just another name for something that exists outside. So now this is a promise that our function will not do anything to change this variable on the outside of our function, okay? Any question about that? And it will be very, very, very common to see const references rather than just references. Yeah? Yes. Yep. Yes. So the const is enforced by demanding, the compiler will demand that every time you use it, so like if you passed arig itself to another function, the function signature of that function would have to be const as well, and so it would not have the ability to change it. Does that help? Did that answer the question? Like, it's pretty smart at matching up what has to be const. And once arig has to be const, it must always be const. Now, can it dig through to heap memory associated with it? I believe it's smart enough to do so, but I'd have to try it out on a complex thing. Okay? Yes? It protects the members of the object, of a rig's object. So you can't have a rig dot anything on the left-hand side of an assignment statement. Okay? All right. Yes? Yep. So the pass by reference, I'm not sure I understand what the confusion is. Pass by reference means a rig is just another name for the thing that this is called on. So for example, if I say sphere A, sphere B is a copy of A rig is just another name for exactly the memory named A. Okay, so a rig refers to A. Okay, now imagine if your copy constructor was such that by making B, you stomp on A, right? Like when you copy A into the space for B, you destroy A. That would be a bad thing, right? So the const is a guarantee that that will not happen. Okay? All right, so if A comes in an apple, it's a promise that A will still be an apple. It won't all of a sudden turn into a banana. I mean, a basketball. It had to be another sphere. Okay, yes? So the question is whether or not we could have the copy constructor have an asterisk here instead so that you're actually copying a pointer. No? Yeah, sphere pointer BC equals what? Ampersand orig. And what value through that pointer? Access the pointer. If orig is constant, oh, here, I don't know. You'd have to go try it out inside the copy constructor you're asking about, right? Go try it out, okay? This is an experiment that you can do, and it's kind of an aside. Okay, so let me write the answer to that, and then we'll keep going, okay? So what does it mean that the copy constructor's parameter is constant? It's a promise that the copy constructor or any other function, you'll see these as parameters for any function, will not change the value of the parameter. Okay? So a rig, nothing about a rig can be on the left-hand side. And the compiler will help you straighten all this out. You'll see this in MP2 as well. Okay, finally, for this slide, why on earth are we talking about this? What is special about our new fancy sphere class that demands that we're having this conversation now? What's special about? Why are we having this conversation now and we never had to do it before? Yeah? Exactly, very good. So all of our stupid sphere, when we talked about this before, it only had stack variables associated with it, right? But now we've got this pointer, and moreover, the pointer is instantiated with heap memory. So it's the fact that our constructors or any other function associates heap memory with our object. Constructor or any other function associates heap memory with the object. Okay? So if there was no heap memory, we would not need a copy constructor. The system provided one, which is a member-wise copy, would be golden, work just fine. Okay, Wade's here with handouts, so raise your hand and he'll help you out. Okay, let's keep going. So all of this is well and good. All of this is well and good, but I think if I were you, I would have this sort of niggling feeling like we've not put away our toys. Because we've been talking about constructors and now copy constructors that allow us to allocate dynamic memory, but we haven't talked about mechanisms for putting away that memory. Now, the first thing we're going to do is investigate whether or not we should worry about it at all. And the second thing is, if we should, what should we do about it? And if we should not, what should we do about it? Okay, so the context of the conversation is the phrase destructors, and so we're going to be talking about what it means for a function to be a destructor and what its purpose is. All right, so we have our same old kind of smart sphere class here, okay? And then I have some code that I would like to trace for just a second. Let's see, so I'm going to declare a sphere A. When I declare a sphere A, the constructor is going to create something that looks like this for me, right? And now I'm going to call my function, which is up above, on A. And A gets passed through the parameter into S. Okay, becomes the value of S. S is set up on the stack to look just like A. Okay, so S now, pretend that S looks just like A. All right, any question about that? What code does that? What code makes that happen? The copy constructor code, that's right. Okay, fine, fine. I'm going to declare another one of these whose name is T, whose type is a sphere, and whose value is initialized to be just like S's. What code is responsible for doing that? again, this should be like, the reason you're not answering is because it's an eye roll, okay? Because it's, duh, it's the copy constructor, okay? Again, the copy constructor is responsible for making this copy of S. Fine. Now we're going to mess around with S and T for a while in the context of the function. Okay, maybe we change this value for S. Maybe we change this value for T. Who knows? It doesn't really matter. But when execution of function myfun is done and control passes back here, here's what happens by default, okay? T is essentially removed from the stack. Okay, the stack moves down, top of the stack moves down, but effectively, T is removed from the stack. And S is removed from the stack, and we're back to the variables associated with the calling function. Now, my question for you is, how do you feel about that? Do you like that? Is that good news? The top of the stack moves down, and that's pretty much all that happens. Is that okay? What bugs you? Something should bug you. What bugs you? Yeah? Yeah. Yeah, look. That data, that memory associated with those spheres that was allocated on the heap by these constructors now has nothing referring to it, right? Those are big, garish, big, glaring memory leaks. So the question is, how do we alleviate this problem? Well, and the answer to that is, I haven't been complete in describing to you what happens when we pass control back. When we pass control back to the calling function, actually, two things are done. A destructor is called, the sphere class destructor is called, and the thing is removed from the stack. Okay, the destructor is called first, and the data is removed from the stack. Okay? Now, what the heck is the destructor? It's this little piece of code that you can control. If you don't write anything here, nothing really happens. But if you write something, then that code will be deployed. So what we're doing is we're writing the code that we would want to be deployed before T and S are T followed by S are removed from the stack. Okay? Question? Because it's the right-hand side, it's A that's not going to be changed. A is a rig, okay? A rig's not going to be changed upon the copy. But the thing it makes can be changed because you're making a brand new one, which is its own self. It's kind of like, you know, a new person, kind of, right? It is its own entity, and it should behave just like a brand new sphere, okay? There's no constraint on how it's used. All right, any other questions? It's a good question. Any other questions about this? All right, so you've had a minute to think about it. How would we free up this memory? If we're trying to free up that memory, what's the syntax for freeing that memory? I'll tell you we've got one of these things. It's created. The system knows which one we're talking about. Our only responsibility is to free that memory. Yeah? You cannot use free. You could, but you won't. You should use C++'s version of free, which is delete. Very good. Okay. We're going to say delete ats, because that's the name for that memory. But we're going to note that we recall, we're going to tell the system, oh yeah, I remember that's an array. Okay, so this is how you free the memory associated with a dynamic array. Okay, any question about it? So now if we execute this code again, I'll do the shorthand version, okay? We've got this set up in memory, and I'll do it in red. When control passes back, T's destructor is called. So the memory is freed, and then the stack, the top of the stack is moved down, or T is taken off the stack. Then S's destructor is called, and S is removed from the stack, and we're done, and there are no memory leaks. Yeah? Yep. Yep. Everything else will be taken care of you just like it was before. Okay? Only heap memory associated with your object needs to be dealt with here. Yes? So the question is, should we set ats to null? And there's really no reason to do so, because it's going to be reinitialized on when the stack is used. You could. Yeah? Yeah? Yes. Excellent. I'm so glad you asked the question. Okay. So do you see what he's getting at here? I can reach this one, so let's pretend it's this one that we're freeing, okay? When we say delete at array ats, the system has to go, okay, I'll delete that for you. But here's the thing. Think about what a string is. A string's probably an object, right? A string really is probably an object that has an array hanging off of it that contains characters, right? So, and you know, this one probably has an array hanging off of it that says shiny in its elements. This one probably has an array hanging off of it whose entries are juicy, right? So whose responsibility is to free that memory associated with those strings? Whose responsibility is it? Who's going to clean up that memory? The string class destructor. That's right. The string class cleans up that memory. And that is known by the system because it knows that this array is a string array. So that's going to happen right before the memory address is given back to the system. Those destructors are going to be called, okay, for you. You don't have to worry about it. Who asked that question? I don't know who I'm talking to. Did I answer it? Okay. All right. Any other questions about this? Yeah? Yeah, okay, so if the string pointer points to stack variables instead, then I believe the compiler will be able to figure that out for you. Because if delete is called on something that is not necessarily on the heap, you get a compile error. Okay? All right, anything else? Yeah? Yep. Yeah, that's one of the beauties of C++, right? So you don't have to remember how many elements you have in the array. You don't have to remember what type of thing it contains. That's a little bit of the bookkeeping that C++ will do for you. You just have to remember that it is an array, and if you forget, the compiler will tell you. So go figure. Yeah? So his question is one of design. His question is one of design, and it invites a long answer. So his question is, why do we keep number of attributes here? That's because we are probably ill-advisedly, like we shouldn't be doing this, we're essentially maintaining this array ourselves. This is really the only way that we know how many elements are in it, okay? That we, at the programmatic level, know how many elements are in it. The system will keep track of how long that array is, but we only know because we kept track of it. What we should be doing, and the reason I say this is ill-advised, what we should be doing is taking advantage of the fact that there is a standard class called a vector that does all of this for you, that has a member function called length, that will tell you how many entries. But what we want you to understand is sort of how these dynamic arrays work. So using vector would be like making it too easy, kind of. Is there a question? Is there a question? Okay. Yeah, Mark? I don't know if it has, I mean, vector is the standard library's implementation of a dynamic array. So I don't know if it has ARRAY. Okay. All right. So there's another instance in which the destructor is used by the system for you. It's the same destructor. I just forgot to put the code in here, so I'll do that again. And that is, well, the following. So this time, we've got a sphere pointer B, and we're going to instantiate it by calling new and asking for a sphere on the heap. Okay? But because this is an example, I'm just going to delete it again immediately. What happens by default on delete is this part is freed by the system. Okay? If you want delete to look more deeply, you have to write your own custom destructor. So we do that, and then what happens upon delete is the destructor is called, and then the memory pointed to by B is freed. Okay? Very similar to what happens with arrays, actually. All right, any question about that? Okay, just another example. All right, so now we have, over the last 2 days, we have the copy constructor and we have the destructor, and they both kind of deal with this stuff that's going behind the scenes, going on behind the scenes that's related to memory, okay? Before we go on, I want to talk for just a second about sort of diagnosing the need for destructors. So a little bit of a summary. The destructor is never called. We provide it for the system to use in two situations. For an object of class A, when the object goes out of scope. A's destructor is called. Okay. The second case is for a pointer to an object of class A. For a pointer to an object of class A, when delete is called on the object, A's destructor is called. Okay? Sorry for the mess. It's kind of good for you to have to navigate the mess, because then you have to think of what words to say. All right. So how do we know if we need a destructor? Again, the story is similar. If your constructor or any other member function of your class allocates dynamic memory. Okay. All right, so I feel like we're done with destructors. Oh, I do have one more thing to say. So there's like this ongoing checklist, and sometimes I talk before I'm all the way to the bottom of it. All right, that's like a synchronization problem. All right, so what do destructors typically look like? They're just usually a sequence of delete statements. Delete, 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 delete. Sometimes MP2, 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 MP2. Sometimes you are controlling your memory a little more, little less abstractly, and you will need to free memory associated with the elements of an array. So for example, if instead of strings we had string pointers, then you would explicitly need to call delete on those strings, for example, okay? So in that case, your destructor would actually have a for loop in it as well, an iterative destroy. Okay, and that will be relevant as you puzzle over MP2. Yeah? Mm-hmm. Yeah, right. It would have to do that. And it would be a matter of whether or not this was null, right? Right? I mean, it's still going to be a member variable. So, all right. Any other questions? I mean, it's almost always the constructor, but sometimes it's not. So I have to say it. All right. Any other questions about all this? Okay. I want to turn the page here a little bit. I'm going to turn the page away from destructors. So what we're going to talk about next, not destructors. Okay. So, but again, we've got our smart sphere class. We still have, you know, our objects still look something like this, but I still have a little bit of a piece of code that I want to trace. All right, so how does this go? I'm going to declare sphere A, okay, and declare sphere B, and I'm going to give A value. Maybe it's the constructor that does it, maybe not, I don't know, it doesn't really matter. So 3.23 red, juicy, crunchy, okay? And now I'm going to do this assignment statement. Okay, that's our focus for the moment. Okay, so B has all of these features associated with it, okay? It will have that by virtue of being a sphere for sure. And now I want to assign the value of A into B. Here's what happens. By default, a member-wise copy is made, which means that I can look at this and go, oh, it's a double. Doubles know how to copy themselves, 3.2. Oh, it's an integer. Integers know how to copy themselves. Oh, it's a memory address. Memory addresses know how to copy themselves. And the result is that. Okay. I don't know about you, but I'm pretty sure that the standard behavior that we accept when we write code is that an assignment statement doesn't tangle up your variables. Okay? It makes essentially independent copies of the same data. All right? Now, we have messed it up. Any question about the issue? All right, once again, it's a memory issue, and it fits very much, it's very consistent with the conversation that we've been having. Now, here's the thing. We don't want somebody writing blue code like that, the client code, to have to change their behavior. So what we're going to do is we're going to redefine that assignment right there so that it works the way we'd like it to. We're going to redefine assignment so that when B equals A happens, instead, in the end, what we get is, you know, what we'd like to see. Red, juicy, crunchy. Okay? Any question about that so far? Dun, dun, dun. All right. Well, I want to step back for just a second and talk about this process of redefining symbols. Another name for that process is overloading operators. The overloading part is the redefining. And the operators part is the active symbols part, the symbols that do stuff. And they're usually symbols, but they're just generally operators. Okay. All right. Now, I assert that you're already pretty comfortable with overloaded operators, okay? So I want to give a little example. I want to ignore this part of it, actually. I want to focus on the A plus B part, okay? Maybe we're outputting it. This is an issue, too. It's more interesting, okay? All right, so I assert that if I declared A and B to be integers, and gave them values, you would know what to do with A plus B, yes? You've probably known this since you were about this many years old, right? I tell you they're integers and ask you, you know, you have 2 pieces of pie, you have 3 pieces of pie, you add them together, yay. But think about it. You also would not be the least bit surprised if I said this, right? You've got 2.5 pieces. You have a piece and a half. Total, you have, right? Nothing about that surprises you. You kind of want to roll your eyes at it. Kind of the same. It's the same thing. But I also think that if I said this, kind of know what to do with that too. Do you? What do you think might happen? How do you add two strings together? Yeah? Yeah, right. That's right. It happens to be the case that when we add two strings together, we just concatenate them. It's a completely different operation, right? It's completely different code that has to execute to do this plus if A and B are strings versus if A and B are numeric, right? And yet, if you had happened to know the default behavior of C++, you would know that that's not a big deal at all. You just concatenate them. Ain't no thing, okay? My question for you is, what do you think about this? What the heck does that mean? All right, so we want to redefine this plus. We want to redefine this plus so that it works if its operands or its arguments are spheres instead. We control spheres. We have the power to do this. Now, before I actually discuss the design process of writing the code, I want to say a little bit more about syntax. We are totally comfortable reading A plus B here, right? Like this is how we read code and math. But the computer does things slightly differently. It goes, oh look, I've got a couple values and I'm supposed to add them. That is, I'm going to pass those values to a function and do some computation on them. So what I'm saying is that A plus B, which is how we see it with our eyes and understand it with our brains, is understood as a function called operator plus with parameters A and B, or alternatively, and this is the one that we're going to exploit, A dot operator plus with parameter B to the system, okay? That is, A is an object. We're going to call the operator plus associated with that class name, and the parameter to that function is going to be the right operand of the operator, okay? Any question about that? And if you take a look, looky, here it is. Here's the declaration of such a function. All right, so let's see. Now it's a design moment. I've got two spheres. I have a golf ball and a basketball. How should I add them together? I have no idea what the sum of a basketball and a golf ball should be. Golf ball, basketball. It probably has dimples and it's an orange. Okay? So what should it be, really? Oh, and let's not make this a fancy sphere. Let's just pretend this is a stupid sphere, okay, just for quickness of discussion. So what should we do? Yeah, go ahead.
I think we should probably combine the volumes together.
Okay. Okay, so combine the two volumes is a suggestion. Perfectly reasonable suggestion. Yeah, another idea? Yeah, right. Combine the radii, which is a different addition. Look, this is a design discussion, right? There is no right answer here. There is only convention and what the client expects and the complexity of doing it in that space in this room. So I'm going to take the second suggestion, which is simply that we're going to return a new sphere whose radius is the sum of the two radii, okay? Now, I'll show you how to do that. There are a couple lines of code that might surprise you here. I want to return something because Cout needs something to return, right? We expect this thing to give us some value. So I'm going to declare a new sphere for return only. Okay, and I'm going to set its radius. It is the current object's radius plus the parameter's radius, and I'm going to return t. Like I said, stupid sphere. Not a fancy sphere. Okay? Any question about that? Yeah? Oh, excellent point. Oh, no. The radius is private. Oh, no. Is it okay? Yeah, it's okay because this is a sphere class member function. This is a sphere class member function, so it can access other spheres' private members. Yes? Very good question. Why are we returning a reference? Because I wanted you to ask that question. And in fact, is it a good idea to be returning a reference here? What's it a reference to? The reference to a local variable which goes out of scope, okay, means we're going to try to access, we're going to try to rename stack memory that has gone out of scope. So that's actually a typo. Good catch. We wouldn't return by reference there. Alrighty. What else? Anything else about this? I think there is one other super interesting thing about this slide. Yeah? Exactly. Really good. Okay, look. We returned a sphere here, so we're kind of done. That's fine. It's not very interesting, but it's fine. Now we've returned a sphere, and it's sitting on the left-hand side of this thing. Cout doesn't know how to output a sphere. What does it do? Spit out bubbles out of the computer, right? Like, it has no idea what to do with a sphere. And so what do you think we have to do? Overload the redirect, right? We have to write a function. In order to make this code work, we would have to write a function that overloads the redirect for the IOStream class. Okay, in fact, there are a ton of things that can be overloaded. These are the things that can be overloaded, and it's a totally different question about whether they should be overloaded. I'll tell you right now that in my coding experience, which granted is not extremely vast, it's been a long time since I've done production C++, I've only really had reason to overload about 5 of those things, okay? So you have to think very judiciously from a design perspective about what the client expects, the way the client code is expected to behave before you decide to overload the operators. Okay, so next time we are going to spend our time talking about overloading the assignment operator. No, we have 2 minutes. I'm going to use them, okay? Really. We can do it even in 1 minute. So, as you know, we're going to overload the assignment operator. I just want to talk for a second about the function signature of the overloaded operator. That function signature is merely intended to characterize that thing, the thing on the right-hand side of the assignment statement. So just like you've seen before, this is going to be a constant sphere reference right-hand side. Now, it doesn't have to be a reference, but it should be because you don't want to make a copy here. It might be expensive to do so. All right, and then we'll talk about the return value next time. See, you survived. Yeah?